Okay, class. So welcome back. So we've been this week uh, been playing with Cauchy sequences. We're going to see something a little different today. But we saw that these were, useful to characterize convergent sequences in R. Maybe I'll just mention. So there's going to be kind of a homework assignment due over Thanksgiving. And part of it will be, so part of it is using Cauchy sequences to actually define the real numbers. Okay, so this is, we've kind of said that the real numbers are this set satisfying these certain axioms. We've never actually given you the set that satisfies and operations that satisfy these axioms. But next to homework assignment, you will see it. Okay, so this is, one other major use and application of these Cauchy sequences. But today we're going to do something slightly different, which is start to look at what's usually called the topology of the real numbers. Okay? Okay, so I want to just start by giving kind of two example theorems, which kind of give an idea of what this topology of the real numbers means. Okay, so I'll just give two theorems. So the first, I think, and you've probably heard of both of these. The first is the intermediate value theorem. So I have to admit that both of these theorems are going to involve continuous functions, which I haven't talked about at all. So it's just going to serve as motivation for what we're going to see today. Okay, so this says, if you have a function from an interval, so it could be maybe AB or AB to R, which is continuous and assumes both positive and negative values. Okay. Has a root. Okay, so then has a root. Okay? So in the picture, if you have a graph of a function, and there is a negative value and a positive value, then at some point you have to hit 0. Okay, and of course that you actually have to hit every real number between between this negative value and this positive value. Okay, so that's one kind of sample theorem, and I'll say first kind of why this is thought of as a topological theorem. The other one is called the extreme value theorem, or the maximum min theorem. Again, it says if I have a continuous function, now I have to be careful about the intervals from AB to R, then the image, okay, f of AB, has a maximum value and a minimum value. Okay, so the picture here, well, it looks something like this. If I have a graph of a function, it attains a maxima. Oh, so here I have the endpoints where the maximum and min. I guess I could have also had a function which looks like something like this. Okay, so there's a maximum value and a minimum value which are attained, right? So there are numbers that you can plug in that attain its both its max and min. So notice that each of these theorems is false, for different domains. Okay, And you can think of, kind of when people say that they want to study topology of the real numbers, it's figuring out the right characteristics of these sets, in both cases of the domains, where these theorems are satisfied. Okay, so for example, let me just remark that if I have a function, say, defined on, -1 to 0, union 1, 2, does not satisfy this. Does not satisfy the intermediate value theorem, because it could, well, on -1 to 0, it could just be a constant function here, and then on 1, 2, it could be the constant function here. Okay, so it attains a positive and negative value on elements in its domain, but never attains 0. Okay? Similarly, the extreme value theorem depends on the domain. So if the domain was the open interval, 0 to 1, then, 0 to 1, sorry. Then we've seen functions which don't obtain a maximum or minimum value, right? So this is a function which has, where the image is the entire real line, or you could have, something like, a function like this, which again doesn't, never obtains its maximum or minimum. So in this case, you can imagine we want to know something like the domain isn't split into two different parts. Here we need a domain that's closed, and we'll see kind of what the right generality to say so that we can have theorems like this. Okay, so let me to start to try to define these sets, I have to define what an accumulation point is. This is kind of the first main definition of today. Okay, so let S be a subset of the real numbers. Okay, then X in R is an accumulation point of S if for any epsilon greater than 0, this set, so it's a little funky, so you take X minus epsilon, X plus epsilon, you subtract the center, okay, and then if this set intersect S, has to be non-empty. Okay, so let me just note here that, well, X may or may not be an S. Okay, maybe or may not be an element of S. That's just, some kind of complication that you have to worry about, right? So when you take this intersection, well, the intersection, if X is in the set S, you're not allowed to count that, right? So you're only looking at, because you're removing that from one of the sets, okay? So the picture is you have X, and you look at X minus epsilon, X plus epsilon, and what you're guaranteed to find for any epsilon is some element of S, okay? But I drew it here. So this is the element that you find is not allowed to be the actual element X. It has to be in the interval, but not the midpoint. Okay? So let me do some examples. I mean, you should think this is, it seems very close to X being the limit of a sequence, which is converging to X. Okay, so we'll see that this is essentially the right idea, but you have to be a little more careful. Okay, so the first example would be, well, any finite set is going to have no accumulation points. Okay, so these are really things that you have to have infinite sets to get closer and closer to this x. Okay. So to do this, well, I'll write it out. So we need to show, or need to find, for any real number, an epsilon. So we need to find for any r and r, there exists some epsilon greater than 0, so that r minus epsilon, r plus epsilon minus r, intersect S is equal to m, to the empty set. Okay? So notice, well, what could happen is r might be an element of S. So usually there's kind of two cases here. Okay? So r is in S. Okay? Since S is finite, there's some minimum value or some minimum distance between r and all the other elements. Okay, so I'll just say there exists some epsilon greater than 0 so that r minus, say, S is greater than epsilon for all S in S. Okay, so you just enumerate the elements. You look at this quantity. Oh, I should say, sorry, for all elements in S that are not R. Okay? So when I plug in R, I do get 0. For any other element in S, I'm getting some positive value. And then there's finally many of those. You just take some number smaller than that. Okay? For R not in S, it's essentially the same argument. There's going to be some epsilon greater than 0, so that r minus S greater than epsilon for all S in S. Okay, again, you look at all the values, or all the elements in S, compare their distances r minus S, and you just take some number smaller than that. Okay, so let me do another example. So, example, n, the natural numbers, have no accumulation points. Okay, so I won't prove this. It's essentially the same proof as we saw for the finite sets. If you take any real number, there's going to be some epsilon greater than 0. So either that real number is in the naturals, and then you can take epsilon to be a half, or it will not be in the naturals, and you just have to take epsilon smaller than the minimum distance to a natural. Okay, and that's going to be, you're going to be able to find such an epsilon. Okay, so let me do another example where there are accumulation points. Okay, so if I look at the set S, which is our favorite set, 1 over n for n in the naturals, then the accumulation points are the set just containing 0. Okay? Again, I'm not going to go through all the details, so you can check that 0 is an accumulation point. This is because if you take any epsilon greater than 0, we can find some 1 over n, so that 0 is less than 1 over n, which is less than epsilon. Okay, so essentially the same proof that it converges to 0 shows that 0 is an accumulation point. For any other real number, well, I'll let you think about numbers that aren't between 0 and 1. Okay, so if there's a negative number, well, I take some epsilon which stays negative. If I'm out here, I take some element with epsilon which keeps me above 1. So for any other real number in 0 or 1, well, either I might be something like, 1 over n. Again, I'm going to be able to find a small enough neighborhood, so which misses 1 over n minus 1 and 1 over n plus 1. Okay? And since, again, when we look at accumulation points, we remove the middle point, that doesn't count in our intersection. Or I'm just some other real number, which is not 1 over n. Again, I'm going to lie between some 1 over n and some 1 over n plus 1, and I just take the minimum distance of that. That's my epsilon. Okay? So this example kind of generalizes to the following lemma. Okay? If I have a sequence, xn converging to x, then x is an accumulation point, actually the accumulation point of the sequence point of the set of the xn's exactly when xn is not equal to x for infinitely many n. Okay, so you have to be a little careful, okay, because I could have a sequence which, is just, 1, 1, 1, and so on. This certainly converges to 1, but 1 is not accumulation point of the set 1. Okay, so 1 is not accumulation point of the set 1. Okay, but if you have a sequence where there's infinitely many terms which differ, then it has to be an accumulation point. Okay, so let me just give you the proof. Okay, so I'll just prove one direction, which is suppose that there's terms that are infinitely many terms which are not equal to the limit. Okay, well then for any epsilon we know that there's some natural number so that xn minus x is less than epsilon for all n greater than or equal to n. Okay, and since the xn's are not equal to x for infinitely many n, well, if I look at the intersection of x minus epsilon, x plus epsilon minus x, intersect the set containing all the xn's, this will be non-empty. Okay, so I can go out far enough in my sequence where this term is not equal to x, and that one will have to be within epsilon. Okay, so let me just quickly restate Bolzano-Weierstrass theorem, and then we'll get to our other main definition of open and closed sets. Okay, so kind of one other way that you see the Bolzano-Weierstrass theorem stated is that an infinite bounded set has an accumulation point. Okay, so this is, you should think this is similar to, the Bolzano-Weierstrass theorem as I originally stated it had every sequence contains a convergent subsequence. Well, if that sequence is a set, and that set, if you make a set with the terms of that sequence, and you end up with infinitely many terms in that set, then that accumulation point will be the limit of that certain subsequence. Okay, so that's essentially the proof. So take a sequence xn, okay, with terms in this set, that are all distinct. Okay, so you can do this since the set is infinite. Okay, by the original Bolzano-Weierstrass theorem that we showed, okay, so by the original BWT, there exists a convergent subsequence, okay, and then by the previous lemma, since all of these terms are distinct, the accumulation, this limit is an accumulation point. Okay, so we found a convergent sequence of distinct terms. Therefore, by the previous lemma, it's the limit. It's an accumulation point of this convergent subsequence. That shows it's an accumulation point of the set that you started with. Okay, so now let me go to kind of our two main definitions for today. Oops. All right, so definition. A set U of the real numbers is open, and you should think this is a generalization of being an open interval. Okay, so it's open if for any x in U there exists some epsilon greater than 0, so that x minus epsilon, x plus epsilon is a subset of U. Okay? So if I have my open interval, say, and I take any point x, what this is saying is I can find a little neighborhood which is completely contained in my set. Okay? So notice, for example, if I take the closed interval 0, 1, this property does not hold, right? Because it's true for a lot of elements, but it's not true for the element 0 or the element 1, okay? So the other kind of complementary definition is that a set V contained in R is closed if the complement is open. Okay, so this is saying if you take any element not in V, you can find a little neighborhood which still misses V. Okay, so let me just make some notes. So for one thing, the empty set and R, are both open and closed. Okay, with these definitions. Okay, so you can easily, for one thing, they're complements of one another, so you just have to check that they're both open. R is certainly open, straight from the definition, and the empty set is open because this condition, the thing that you have to check is vacuous. Okay, so they turn out to be the only sets, or subsets of R, which are both open and closed. Okay, so you kind of have to, these are just cases that you have to worry about. Okay, you can also have sets do not have to be open or closed. Okay, so for example, the half-open interval, you can check is not open, but neither is its complement. Okay, so its complement would be 1 to infinity union 0 minus infinity. Okay, and this won't be open. Well, the set 0, 1 won't be open because of this endpoint essentially, and this interval won't be open because of that endpoint. All right. So I think this will be a lecture problem is that you should show AB, so the open interval AB is open with this definition, and the closed interval is closed. All right. So I'll give a couple properties of these. I won't prove any of them. They follow basically immediately from the definition. Okay, but they give you an idea of what you should expect these open sets to be. Okay, so I guess I'll say a lemma, a union, so an arbitrary union of open sets is open. A finite intersection of open sets is open. Okay. From this and De Morgan's law, you get that an arbitrary intersection of closed sets is closed. And similarly, a finite union of closed sets is closed. Okay, and when I mean, and it's in both cases, if you take an infinite intersection of open sets or an infinite union of closed sets, you can get something which isn't open or closed anymore. So just maybe I'll just note, if I take the interval -1 over n to 1 over n, this is, well, each one is an open set, but if I take the intersection, I'm getting a single point 0, and you can check that points are closed, okay? Okay, so I'm taking an infinite intersection of open sets, and I produce from that a closed set. Okay, similarly, if you look at, say, the interval from 1 over n to 1 minus 1 over n, and take the union, then this will be precisely the open interval to 0 and 1. Okay? So you can take again, countable union of closed sets is going to be, in some cases, open. I mean, and then also in some cases it's closed, and you just lose control completely. Okay, so I want to prove a lemma which kind of relates these two concepts that we've seen. Okay, and then I'll state and give an idea of a proof of kind of one of the main theorems that's used, or that comes out of this. Okay, so first, the lemma says that a set X, or subset X of the real numbers, is closed if and only if it contains, so X contains all its accumulation points. Okay? So you can, go back to these intervals and kind of check that this is right. Okay, so the accumulation points of this interval will turn out to just be any point in the interval. The accumulation points of this one will be the closed interval AB, so you miss some accumulation points. All right, so let me give the proof. It's pretty much straightforward from the definitions. Okay, so let me just say, assume X is closed, and let X, I mean, that's a bad, let me say, let Y in R minus X. Okay, so I guess I'm doing this direction. So we have to show that Y is not an accumulation point. right? So if again, we're not saying that every element of X is an accumulation point of the set X, but certainly if you can show that any element not in X is not an accumulation point, then X must contain all of its accumulation points. Okay? So since X is closed, I can say since R minus X is open, there exists some Y, or some epsilon greater than 0, so that Y minus epsilon, Y plus epsilon is contained in R minus X. Okay? In other words, if I take X, intersect it with Y minus epsilon, Y plus epsilon minus Y, well, this is strictly smaller than the interval, so it will still be empty. Okay? And therefore, Y is not an accumulation point. Okay? So notice that what this is saying is X is closed, its complement is open around. That means that in any point in its complement, you can find this little neighborhood, which still is in the complement. That shows that it can't be an accumulation point of the set. Okay, so now let's show the other direction. Okay, so we're going to show the contrapositive. Okay. So we're going to assume X is not closed. Okay? So notice you cannot assume that X is open, right? That's the tricky part here. Okay, since you can have sets that are both, not open and not closed. On the other hand, what you can assume is that R minus X is not open. Right? So in other words, there exists some, again, Y in R minus X, so that for any epsilon greater than 0, this interval Y minus epsilon, Y plus epsilon is not contained in R minus X. Okay? So in other words, this means for any epsilon greater than 0, the interval Y minus epsilon, Y plus epsilon intersect X is not empty. Okay? But then, since Y is not in X, we also have Y minus epsilon, Y plus epsilon minus Y intersect X is not empty. Right? Because notice, well, any element in this intersection has to be an X. So it can't be Y. And so therefore, if you remove Y from one of the sides, you're still going to have a non-empty intersection. So therefore, Y is an accumulation point of X, but Y is in the complement. Okay? So therefore, X does not contain does not contain all of its accumulation points. Okay, so now let me give kind of another important theorem, okay, in this topology of the real line subject. It's a little hard to motivate, I think. So maybe in the next lecture I'll give you some applications of it. Okay. It's called the Heine-Borel theorem. So it says let S in R be closed and bounded. Okay? Then given a collection of open sets UI, so that S is contained in the union of the UI, then you can find some finite subcollection where S is in the union of just finitely many. Okay? So typically the way that you think of this is the UIs are some cover. I'm drawing open intervals. They could be open sets in general. Okay? Okay, this picture was pretty terrible. Let me say U1, U2, etc. Okay, so you cover any of your closed bounded set by open intervals. It turns out it's actually contained in finitely many such intervals. Okay? So notice this is false for open intervals. It's also false for closed but unbounded ones. So notice that 0, 1, for example, is the union from 1 over n to 1 minus 1 over n, right? But if you take any finite collection, then you certainly won't get 0, 1 to be the union, right? These are all contained in one another, so you'll just get whatever one was largest. So you really need infinitely many to get the entire open interval 0, 1. This can't happen for something like the closed interval. Okay? So let me give you kind of the sketch of a proof, and then I guess we're good for the day. So I'll try to prove this for S being just the open interval, the closed interval AB. Okay? So the picture I had is essentially the same one I'll use, where we have these sets which are contained in the union. There's presumably infinitely many of them, and we have to show that we can cover the interval with only finitely many. Okay? So let me just let B, be the elements in AB, okay? So that the closed interval A to X is covered by finitely many U sub I. Okay, so I'm assuming I have this cover S in the union of the U sub I's. Again, I don't know anything. It might not even be a countable collection, so I'm just get some index set there. Okay? What I'd like to, and I'm looking at the real numbers in here so that the closed interval from A to X is covered by finitely many. What I want, of course, is that B is in B, okay? Because then I would have covered the entire interval AB with finitely many sets, okay? So notice, of course, well, so first, B is obviously an upper bound, okay, for B. And also notice that A is an element of B, okay? Since you just take, since you can take any interval, AA, which is just A, is in some UI. Okay? So now we do kind of a similar trick to what we saw for nested intervals, where you had these intervals converging to something and you just take the supremum of some endpoint. In this case, you let C be the supremum of B, and we'll show that C is in B, okay? And, well, eventually C is equal to B. Okay, so let's show that C is in B. Well, we do know, so we know that C is in some UI, okay? So maybe I'll just draw the picture here. We have C, some UI, which I'm going to assume, let me just assume that this looks like C plus, C minus epsilon, C plus epsilon. Okay, I can always find inside of UI a small neighborhood which looks like this. Okay. Then since C is the sup of B, well, I can find some element here. So there exists X, which lives in C minus epsilon, C plus epsilon, okay? Therefore, by assumption, we know that AX is covered by finitely many open sets. So U1 up through UN. Well, and now we have this open set UI which contains C, so you just throw that in, okay? So therefore, U1 up through UN union this new set UI covers AC, therefore C is in this set B that we're interested in. Okay, so now we want to show that C is equal to B, and then we're done, okay? Right, because we've defined B to be these elements so that A to X are covered by finitely many things. We've shown that the supremum of the set is in there, so if the supremum of the set is B, then we've covered A to B with finitely many sets, okay? And it's a similar argument, okay? So suppose that C was strictly less than B. Okay, so again, I'll draw this pretty much the same picture, A, B, and C, okay? Then we know that C, so AC is contained in some union from I equals 1 to n of the u sub i's, okay? And therefore, we know that C plus epsilon is also contained in this union. Okay, because this is the defining property of these sets being open. Okay, so I can find some little neighborhood which is still contained in the union of these open sets, okay? Okay, so there exists some epsilon. On the other hand, we can just take epsilon small enough so that it lies between C and B. Okay, and therefore, we have covered say A through C plus epsilon over 2 by finitely many open sets. So in other words, C is not the sup, Okay, and that's the contradiction. Okay, so essentially the idea is, you keep kind of progressing further and further out, and as you kind of travel through these u sub i's, and what the openness condition tells you that you can always just continue a little epsilon more, okay, until you're forced to reach b in only finitely many tries, okay, or finitely many sets. Okay, so I'm going to stop here. Thanks.